So far we have seen the theory of linear regression, right. So now we look into the implementation of linear regression using MATLAB. Again, as we have been stressing from the beginning of the course, here we are using MATLAB. You are free to use any other software. So this is the so we'll initially begin with simple linear regression problem, right. So wherein we have this x and y data is given, right. So this is our independent variable, this is our dependent variable, right. So we have here 7 points, right, and we want to fit this model y is equal to a naught plus a1 x, right. So in MATLAB the function that we will be using is regress, right. So before using regress, let us just try to get this plot in MATLAB. So as you might already know, CLC helps in clearing the command window. Clear will help us to clear the workspace of MATLAB, and close all will lead to closing all the currently open graphic windows, right. So now we define the vector x and y, right. So this is nothing but just the definition. So this semicolon makes sure that we get a column vector for x and column vector for y, right, and then we use the plot function. So when we say plot x comma y, if we just say plot x comma y, what would happen is we would not get such a plot, but we would get a plot wherein all these lines are connected. So we do not want that to happen, we just want the points, right. So that is what we are doing is we are saying plot x comma y comma this again within single quotes, over here it is within single quotes. So this B stands for blue and this dot stands for placing a dot. So what we are asking MATLAB is to just put a blue color dot wherever the points are there, right. So we would get a plot similar to this, and this helps us to add the label. So this is x label. So we just want to write x and y for the x axis and the y axis, right. So again we give this in single quotes. So whatever we give in single quotes will be replicated as such. So if we have given let us say x label, within single quotes if we had given temperature, right. So temperature would have been written over here, right. So this piece of code will help us to just get this plot, right. So far we have done, right. So for linear regression, the function in the inbuilt function of MATLAB is regress. So for regress we need to give the dependent variable comma independent variable, right. So independent variable, it can be multi-variable also. So regress can do simple linear regression, multilinear regression, and we can even use it to do polynomial regression, right. So we need to give independent dependent variable comma all the independent variables. In this case we have only one independent variable x, right, but the model that we want to fit is a naught plus a1 x, right. But this regress function is based on the general linear least squares which we have discussed previously, right. So there if you remember, we have to stack the independent variables with a column of ones, right. So if our model has an intercept, right. So in this case we want to fit a model which has an intercept. So what we need to do is we need to give a column of ones. So this is what we want to construct, right. Since there are 1, 2, 3, 4, 5, 6, 7 data points, we want this a column of ones, right, with 7 rows, right. So to get that we will use this ones function of MATLAB, ONES. So ones function of MATLAB can be used to generate as many rows and columns that are required. So right now we can actually say 7 comma 1, but if we change this x with 10 values, then again we need to go and do this, right. So instead of writing this number 7, what we will say is ones of length of x. So even if this vector x changes, it will measure the length and then it will appropriately select, right. So that is what we are doing. Ones of the number of rows that we want is nothing but length of x. The number of columns that we want is one column, right, because this is what we want. So this is number of rows, this is number of columns, and this is the function. So this will just give us a column of ones. So how many rows? 7 rows, because the length of x is 7, and then we are stacking this x vector. So basically what we are doing is 152, 147, 166, 170, 159, 173 and 169, right. So this is what we are constructing as capital X, as uppercase X, right. So once we have constructed this, we are ready to use the regress function. So here we need to give regress y comma x. So this regress function can return a large number of values. All of them have their own significance, but in this case, but in our course we have restricted ourselves to finding out this model coefficient and the coefficient of determination r square, right. So basically regress actually gives us 1, 2, 3, 4, 5 output arguments. The first argument is the coefficients, right. So it is not necessary to write b, we can write any variable name, right. So we have chosen to write b, you can write any variable, and these 3 arguments, the next 3 arguments, because of whatever we have in the whatever we have covered in this course, we are not in a position to interpret that. So we are not receiving those values, but if you wanted those values you can just say b comma c comma d comma e or whatever appropriate variable names, and stats. So stats is again a variable name, you could have given any other variable name over there, right. So when we do this, so this line will help us to solve the regression problem, and the coefficients would be returned, and stats will be a vector, right, and the first value in the vector stats will correspond to the r square value, right. So stats is going to give us a number of values. The first one is what we are interested in, right. So once we have obtained the coefficients and the regress function, right, we also want to plot the line. So as we had seen previously in that Anuskum's data, for at least for linear regression, simple linear regression, it is always a good idea to have a look at the plot, right, rather than merely relying on r square value, right. So in order to plot that, what we want is, we want the points as well as the straight line, right. So we want something similar to this, right. The points are also need to be there, and we also need the line. So what we are going to do is, so since we are going to plot on the same plot, we are going to use this hold on, right. So that means it will plot on the same plot where we had plotted the data points, right. So now how do I get the straight line? So for straight line we need 2 points, right. If we have 2 points we can draw a straight line. So x1 y1 and x2 y2. So what we are going to do is, so this y1 and y2 is from the model, right. Once this regression problem is solved, the model coefficients are in this variable b. So what we will do is, for x1 and x2 we will say the minimum value in this vector is going to be our x1. So that is what we are doing over here. So the minimum value of x is going to be our x1, and the maximum value of x is going to be our x2. So the line is going to span from this point till this point, right. So once we have decided on the x values, x1, x2, we can calculate y1 and y2 because we know the model coefficients b, right. So this model coefficient will have as many elements, as many columns in this x matrix, right. So in our case we have 2 columns, so it will consist of 2 values, right. The first value would be the constant value because we have stacked 1 over here and the independent variable x over here. So it is 1 comma x. So this coefficient of x will be the second element, and the constant coefficient will be the first element, right. Had we interchanged these 2 columns, the values in b what we have got would also be in that order. So we would not get a naught comma a1, we would get a1 comma a naught, right. So if we give 1 comma x, we are going to get a naught comma a1, right. But if we had given x and 1, the coefficients would have been in the order a1 and a naught, right. So right now this is the convention that we have used, right. So the model is actually b of 1, so the first value of 1 plus the second value of b and multiplied by the x values, right. So x is a vector now, right. So we will get 2 values for y plot, right. Again this x plot and y plot are just variable names, you could have even given xx yy, right. So since we are going to use it for plotting, we just wrote x plot and y plot, right. So now we have calculated the x1 x2 over here, it will directly calculate y1 y2, it will calculate 2 values because x plot is a vector, right. So then we can plot, we can use this plot function directly to say plot x plot comma y plot, right, with a red color line, right. So here we are not saying r dot. If we had said r dot, it would have plotted this particular point corresponding to this and this particular point corresponding to the end, right. But since we wanted the entire line, right, we are giving just r, right, we are not specifying any symbol next to r, right. So, it will plot a red color line. So, once we are done with that, we will be able to see the points as well as the model on the same plot, right, and then we can add a legend, right. So, legend, so remember MATLAB is not going to decide whether this is the data point or this is the model, right. So, we need to specify that. So, since we started with by plotting the points, right, we say the first thing that we plotted is measured. So, it is going to take this blue dot for measured, and then the second thing which we plotted was the model, right. So, we write measured comma model within single quotes separated by a comma. So, we will get this legend also, right. So, that is how we plot, and if we type just b in the command window, right, we will get these two values minus 10.9167 and 0.4390. Similarly, if we type stats in the command window or any variable name that you had used over here, we will get this 4 values, right. All these values do have their own significance, but since we have not covered that as part of this course, we will only explain what is the first value. So, the first value stands for the coefficient of determination r square, right. So, as you can see, it is very simple to use the regress function for simple linear regression. Again, as we will show, even for multilinear regression, the procedure is rather very straightforward, right. So, now let us look into how to solve a multiple regression problem using the same regress function in MATLAB, right. So, here we have this problem wherein the model that we have to fit is this y is equal to alpha x1 power beta x2 power gamma, right. So, this is a nonlinear model, right. Either we can directly solve this as a nonlinear regression problem, or we can use any one of the data transformation technique that we have seen previously, okay. So, y is the dependent variable, x1 and x2 are the independent variable. So, x1 x2 are the independent variable and y is the independent variable, right. So, here we have 1 2 3 4 5 6 7 8 9 points, right. So, what we will first do is we will linearize this model, right. So, to linearize this, we can take ln on both sides, right. So, this equation becomes ln y is equal to ln alpha plus beta ln x1 plus gamma ln x2, right. So, this is the linearized form, right. So, since we know y, ln y can be calculated, right. So, ln y we will represent it by this notation y, right. So, and this one if we see, this is a naught, right, plus a1 ln x1 can be calculated. So, we will call this as x1 plus gamma, let us say that is a2 is capital X2, because we know this x2. So, we can calculate ln x1 and ln x2. So, once we have calculated that, this model becomes this one, right. So, now this if you see, it is the typical linear regression model which we have discussed previously. So, first for implementing in MATLAB, we will have to specify the data points, right. So, CLC is again to just clear the command window, clear will help us to clear the workspace. So, we are defining these 3 points, right. So, ln y, ln x1, ln x2 we are not calculating, we will just use MATLAB to calculate that, right. So, we have defined all the 3 vectors, right. Then we say that the uppercase y, the variable y is nothing but log of y. So, remember in MATLAB the natural logarithm is actually log, right. Whatever I was referring, whatever we have referred as ln is actually log in MATLAB, right. So, the variable capital X1 is log of the variable X1 and capital X2 is log of X2, right. So, now we have all the data in the transformed space. So, we have this y, we have this x1, we have this x2. Right. So, then we will do the same thing, right. So, till this we have discussed, right. So, here our model actually has a coefficient, right, and regress function needs the dependent variable comma all the dependent variable. Does not matter whether we have one independent variable, 2 independent variable or 100 independent variable, all of them have to be stacked, right. The rows are the data points, the columns are the independent variables, right. So, in this case what we actually want as x is, so we will define the convention, right. So, for this code the convention is the constant term a naught, and then we will have a1 the x1 coefficients and the x2, right. So, for a naught we will have to stack a column of 1s, we will have to have a column of 1s. So, how many 1s do we need? Depends on the length of x1, right. So, the same thing what we used previously. So, this will calculate the length of x1, it will generate that many rows because and one column, right. So, this will just give us a column of 1s, and then we stack the variable x1 and the variable x2. Remember the variable uppercase x1 and uppercase x2, right. So, now we are working with this 3, and then we give it into regress, right. Once we execute this code, again we will get those 5 variables, these 3 variables again we have not seen how to interpret this. So, we will get the coefficients in the variable b and the statistical parameters in the variable stats, right, and we are interested only in the first value of stats because that corresponds to r square, right. So, once we have determined that, right, here we are not going to plot it because we have x1, x2 and y, right. So, we will not plot it, right, but our task was to actually find out what is alpha, beta and gamma. What we have found out is a naught, a1 and a2, right. So, if you remember the transformation which we did, that a1 actually corresponds to beta and a2 actually corresponds to gamma, right. So, beta is nothing but the second value, gamma is nothing but the third value, second value and third value because x1 is the second column and x2 is the third column, right. So, alpha is actually we have used alpha is equal to, so in previous slide if you have seen this is ln alpha is actually a naught. So, ln alpha is a naught, right. So, now we have a naught, we want L alpha, so we take exponential of that, right. So, that can be done using the exp function of MATLAB, right. So, now we have alpha, beta and gamma, right. So, we have got the parameters which we had set out to find, right. Once that is done, since I am not will not be able to plot, let us actually see that for each of this x1 and x2 what would my model give, right. So, that can be determined by this expression, right. So, this is nothing but the values obtained by model, any variable name we have chosen as y model is equal to alpha, because that is what is our model, alpha into x1 to the power beta multiplied by x2 to the power beta, right. So, this will give us the value of the model at each of these points, right. Whatever the number of points are there, for each of those points we would get the y values from the model, and we already know what are the y values which were given to us, right. So, this is just a comparison of that thing, right. So, after this you could have just written y model in MATLAB. So, it would have displayed something similar to this, right. So, for the so this will help us to kind of see how the fit is, right. Since we are not plotting over here, from here we can see, right. So, more or less the fit seems to be good because this column and this column are more or less kind of similar, right. So, and we can also have a look at the first value of stats, right. So, if we just type stats over here, it will give us these 4 values, right. So, the first value is our regression. So, this e power minus 01 stands for 10 power minus 1. So, the r square is actually 0.99992, right. So, it seems to be a very good fit, right, and the model is obviously y is equal to alpha is 36.28, right, x1 power beta, so that is 2.63, x2 power gamma which is 0.53, right. So, this is what we will get from the model. So, for any x1 and x2 for which we do not have the value of y, so for example x1 is equal to again it has to be in the same domain. So, let us say x1 is equal to 0.4 and x2 is equal to 0.04. We can use this expression to find out the y values. So, that was one example for multiple linear regression. Now, we will look into another multiple regression problem, right, but this time we will not have a constant coefficient, right. So, both the examples which we have seen so far had a constant in the model, right. So, that is why we were stacking a column of 1s and then we were stacking the independent variables, right. So, the next model which we are going to consider is not going to have a constant coefficient, right. So, here again 2 independent variables x1, x2, these are the y values. So, these values are given to us and we are expected to fit this model. So, our task is to find out the values of alpha and beta for which this model would best represent this data. So, again we will linearize it, right. So, we will take ln y is equal to alpha ln x1 plus beta ln x2. So, if we use the variable capital Y to indicate ln y, a1 for alpha, a2 for beta, capital X1 for ln x1 and capital X2 for ln x2, right. So, we basically end up with this model, right. The only difference is previously we had a naught, it was a naught plus, right now we do not have this constant coefficient, right. So, it is going to be exactly the same except that for determining the x matrix which has to be fed into the regress function, we will not stack it with a column of 1s, right. So, again these are exactly same what we have discussed, clearing the workspace and the command window, defining the data, transforming the data, and then we determine capital X1 which is x1 and x2. Here we are not stacking ones of length of x1 comma 1, right, because we do not have constant term in our model itself, right. So, the same way that we have been calling this regress function, it is same thing, whether there is a constant coefficient or not, the regress function remains the same. Whether there is a constant coefficient or not is to be captured for this variable x, right. So, we give, remember it is dependent variable comma independent variable, usually we are accustomed to write x comma y, if you do that you would get an error, right, and it would probably tell you why, the reason why you get that error. Unlike the previous case where there were 3 values, now we will have only 2 values, this a1 and a2, right, and a1 and a2 directly correspond to alpha and beta, right, there was no transformation of them. So, this is alpha, this is beta. So, similarly like last time we can also calculate y model, again this is some variable name which we have chosen, right. So, x1 to the power alpha, x2 to the power beta, right. So, this can be calculated because once we are done with this step, right, we actually know the coefficients, right, and alpha and beta are defined here, right. So, we will be able to calculate the y model values, right. So, again if you do y model, you will be able to see the values which are given to us y and what our model is predicting, right. Over here you can see that the difference is significant, right, in this. So, the r square is not going to be a very high value, right. So, again if you type stats in the command window, the first variable, the first value corresponds to r square. So, r square in this case is 0.4936, which is not a very good value, right. Okay. So, now that is about multilinear regression, right. So, now let us go to polynomial regression. So, polynomial regression can be done in 2 ways. We can either use the regress function itself, or there is a separate function called as polyfit, right, that can also be used, right. So, we will see both of them, we will start with the regress function and then we will also look into the polyfit function, right. So, this is the polynomial that we are required to fit, y is equal to a naught plus a1x plus a2x square, and these are our data points x and y, right. So, here we have 6 data points, right, and this is the y, these are the y values, okay. So, the first task is to define whatever is required. So, again clearing the command window, clearing the workspace, closing all the actively open plots, the x vector, the y vector, we are just defining them, and then again since we want only the points, we do not want them to be connected by a piecewise linear function, right. So, we just give plot x comma y within single quotes, right, b dot. So, it will put a dot, blue color dot at wherever the points are there, and then we add the x and y label. So, to get this x and y. So, now we have the data points on a plot, right. So, this is what we have discussed so far. So, our model is y is equal to a naught plus a1x plus a2x square, right. So, what we will do is we will say, we know how to do multi regression. So, we will convert this into multi regression, we will say this is y is equal to a naught plus a1 x1 plus a2 x2, right. So, the variable x2 is nothing but the variable x squared, right, each value squared, that would be x2, right. The capital X1 is nothing but the x that we have received, right, and since we have a constant coefficient, we need to stack a column of ones, right. So, whatever this polynomial regression is there, that we have converted into multilinear regression, right. This we had seen even previously, right. So, this part now by now you should be comfortable with. We measure the length of x, create as many rows involving ones, then we have this x and we have this x square, right. So, we will have 3 columns. So, the first column would be 1, the next column would be 10, 20, 30, 40, 50, 60, and then would be 10 square is 100, 400 and so on, right. So, that would be what would be in x, right, and again this is the same way we are accessing the regress function, right. These two are variable names which we have used. Regress is the function, dependent variable comma independent variables, right. So, here we will give this x which we have constructed in the previous line, and then since over here we have only x and y, we can actually plot and visualize the model, right. So, since we want to do it on the same plot, we do hold on, right. So, whichever plot is this active plot on the same thing we are plotting, right. So, when we were doing linear regression, we needed only 2 points to fit a straight line, right, but now we are fitting a polynomial, right. So, 2 points are not sufficient. So, what we are doing is from the minimum value of x to the maximum value of x, we are generating 1000 points linearly spaced, right. So, what we are doing is between this 10 and 60, that is the min and max, between this 10 and 60 we are generating 1000 points. So, at each of this point we will use the model to find out the y value. So, that will help us to visualize the model, right. So, otherwise if we are going to do 2 points, then we will just get a straight line, right, but the model is not a straight line, right. So, that is why we are generating 1000 points. So, again the first value, since we know the order in which we gave these columns, we also know in what order will we get the coefficients. So, the first coefficient B1 is going to be the constant coefficient, the second one is going to be the model, the coefficient of x, and the third value is going to be the coefficient of x square, right. So, that is why we do B of 1. So, the first value which is constant plus B of 2 which is nothing but A1 multiplied by x plot. X plot is the points that we generated plus B of 3, so A2 into x plot. So, these points, each of the points squared, right. So, this will give us y plot. So, x plot will have 1000 points and y plot will have 1000 points. So, now if we plot x plot and y plot, these are actually 1000 points over here, but since they are very closely spaced, it seems like a continuous curve, right. So, a better way to do this was plot x plot comma y plot comma, let us say r dot and then close the bracket, right, within this single quotes r dot. So, we would have actually got points, right. So, that is a better way to do it than this one, right. So, similarly like last time we did legend, right, first we had plotted the measured values. So, we give measured and then we we plotted the model. So, we give measured comma model. So, we will get this legend also over here. Then we can, if we type B in the command window, we will get these 3. So, the model is actually 34.2, right, plus A1 is 0.1014x plus A2 is 0.0007 x square. So, this is our model. So, for any value, so for example, for 25 we do not have a value of y, right. So, we can plug in 25 over here and we can calculate the value of y. So, the first value of stat is what we are interested at, it corresponds to r square. So, we can just say stats, it will display all the 4 values, or we can just say stats of 1, stats of 1 in the command window. If we had done this, then it would only give 0.9874, right. So, this is how we do polynomial regression using the regress function, right. Remember we said like for polynomial regression there are 2 ways in MATLAB with which we can do. One is using the regress function and the other one is using polyfit function. What we saw now was the regress function, we can now look into the polyfit function, right. So, this is the code that we currently discussed, right, and this is how what we are going to do using polyfit. So, the syntax for polyfit is x comma y comma n, right. So, remember here it was the dependent variable comma the independent variable, here it is the other way. First we need to give the independent variable, then the dependent variable and the order that we want to fit in, right. So, here if you remember we are actually working with y is equal to a naught plus a1 plus a1x plus a2 x square, right. So, we want to fit a second order polynomial, right. So, that is the order of the polynomial, right. So, this CLC clear close all you know, here we are defining just the data points, right, and since we want a second order polynomial we said n is equal to 2. Again similarly we are plotting the data points, right, adding x label and y label, and then we are using this function polyfit, right. So, polyfit can return only the coefficients, it does not give us an r square value, right. So, we are using this polyfit, we are saying x comma y comma n, right. So, n has been defined here to be 2. So, for this same data we can also fit a third order polynomial, right. So, for example, if we wanted to fit y is equal to a naught plus a1 x plus a2 x square plus a3 x cube, all that we had to do was instead of n is equal to 2 we need to say n is equal to 3. Remember, unlike in regress wherein we were forming this matrix X by stacking a column of 1s and then having x values x square, we do not need to do that for polyfit function, right. So, we have this coefficients. One thing you need to remember is the order in which we get the coefficient is the reverse as what we have what we would obtain in regress, right. So, in regress the model was 34.2 plus the first value was 34.2 because the ones were stacked there, plus 0.1014 x plus 0.0007 x square, right. Over here B is arranged in the reverse order, right. So, that you need to be careful about it, right. So, when you are interpreting this B values, the last term is the coefficient, the last but one term is the coefficient of x, the last but second term is coefficient of x square and so on, right. So, that would be B. Again this hold on is same thing, we want to still visualize it. This x plot is also the same thing. Y plot, here we were actually constructing the model, right, because this was our model y is equal to a naught plus a1x plus a2x square, right. Here we can directly use a function called as polyval, right. So, polyval, the input to the polyval is the coefficients of the polynomial which is actually in beta and the points at which we want to find the y values, right. So, x plot is the 1000 points which we generated, remember between 10 and 60 we are generating 1000 points, right, linearly spaced points. So, those points are in x plot. So, the syntax for polyval is give the model coefficients followed by the points at which you want the value of the dependent variable, right. So, this will give y plot, right, again plot x plot comma y plot, again we should have actually done comma r dot this, right, and then we add this legend measured comma model. So, if you run this you would so if you execute this program you will still get the same plot which we got in regression, right. So, the good thing about polyfit is we do not need to compose this X matrix. Another feature of polyfit is that you can directly use this polyval to plot the y values. Again you do not need to explicitly state what is the model as we did in regression, right. But to the best of my knowledge polyfit does not give us the r square value, right, whereas here using regress we can also get the r square value. So, the choice is yours, I mean depending upon the situation you can either choose to use the regress function or you can choose to use the polyfit function, right. So, so far what we have seen is how to use a regress function for simple linear regression. For multilinear regression we saw how to use it in the presence of constant coefficient and in the absence of constant coefficient. Then for polynomial regression we saw it can be done with for polynomial regression we saw that it can be done using the regress function as well as it can be done using the polyfit and polyval functions, right. So, in all these cases we were working only with linear models. Even if the model was nonlinear, we transformed. Remember the couple of problems wherein we had ln function to transform it into linear form, right. So, now we will look into the function n-lin fit, right. So, that can be used to directly solve a nonlinear regression problem. Right. So, in this case we have been given this data x and y, right, and we have been asked to fit this model a naught into 1 minus e power minus a1 x, right. So, this NL fit also requires initial starting point. So, just like for all nonlinear equations you need a starting point, for nonlinear regression also we need a starting values, right. So, a naught is equal to 1, a1 is equal to 1. So, this is what we are going to start with, right. So, these are not optimal values, right. So, that is the task of the function n-lin fit to come up with better values of a naught and a1, right. So, the way to go, the way to do it is first we need to define the data points. Before that CLC clear close all as usual, right. So, this is the guess that we are going to work with. A is equal to 1 comma 1, 1 comma 1 we have chosen the convention to be a naught a1, right. So, wherever we get the values, the first value will correspond to a naught, the second value will correspond to 1. So, if the initial guess instead of 1 1 had to be had it been 0.8 and 0.2, then we would have given, instead of 1 1 we would have given a is equal to 0.8 and 0.2. So, it is important to have a convention and stick to it throughout the problem. So, we will stick with this a naught comma a1. We will define a variable fun, right. It is actually a function handle. So, we have a function whose name is prob, right. We will look into that function, right. That function we have this @ symbol before this prob, right. So, this basically means that we have a function handle whose name is fun, right. So, whenever we use this variable fun, we are actually referring to this function prob, right, prob. It will receive two variables a and x, right, and it will return f. So, what it basically means, that if you give a naught value and a1 value in a, right, and if you give this x points, it will give y, not this y, but the y as per the model, right. So, that is what we are writing here. So, the model is we could have chosen y and y over here, right. So, y is equal to a naught, right, but MATLAB the index in MATLAB starts from 1. So, a of 1, right, a of 1, because that is the convention that we have chosen. So, first value is a naught. So, a naught into 1 minus exponential minus a1 x, right, a1 x, here we are writing a of 2 because the second value actually corresponds to a1, right. So, if all this is confusing, you can just work with alpha and beta, right. So, here also it is alpha beta, right. So, the first value is alpha, the second value is beta, right. So, that way we can calculate y. So, the purpose of this function is, given any values for a naught and a1 and the data points, it will tell you what is the value of the dependent variable, this function will tell. So, x in this case it is 5 data points, right. So, x is going to be a 5 cross 1, right, and a is going to be 2 cross 1 because we have 2 parameters, right. So, after that so that is how this function is going to help us, right. So, when n-lin fit is going to solve this problem, it is going to repeatedly call this function multiple times. You can see that by removing this semicolon and solving the problem, right, you will get y being printed repeatedly in the command window. Okay. So, coming back to our problem, right. So, here we are just merely plotting the data points and just giving the variable labels, right, x label and y label. So far remember we have not started solving a regression problem, we have just defined whatever is required. Okay. So, we have discussed so far, right. So, it is the same thing that we have discussed, right. So, the syntax for n-lin fit is, right. So, the independent variable followed by the dependent variable followed by a function handle, right. So, here it is fun because the problem that we have is actually in written in the function fun, right. So, we wrote it in prob, we have assigned that to fun, right. So, the independent variable, dependent variable, followed by the function where we have the problem returned. So, this is the problem that we have, comma the initial guess, right. So, if you had 5 variables, let us say if you had a problem involving 5 parameters which have to be determined, then A would be a 5 cross 1, alright. So, the output of NLin fit we are receiving in a variable called as beta, right. You can give any variable name over there, right, and we also want to plot the model. In addition to the points, we want to plot the model. So, we have this hold on. Again, as usual, from the minimum value of x to the maximum value of x, we are generating 1000 linearly spaced points, right, and then what we are doing is, so that will give us x plot, right. So, the beta will have the model coefficients, right, model coefficients, it will have as many values are there in this initial guess, right. If there had been 3 values, beta will be a 3 cross 1 vector, right. The first value will correspond to this first variable, the second value will correspond to this second variable. So, if we had, let us say 3 variable alpha, beta, gamma, that is how the guess we gave, let us say 0.2, 0.7 and 0.1. Then beta will have 3 values, the first value will correspond to the optimized value of alpha, second value will correspond to optimized value of beta, and the third value will correspond to optimized value of gamma, right. So, once we have this, now we need to find out what is the coefficient, what are the values of the dependent variable y if the model coefficients are as given in beta, right. So, beta, if we type in command window, we will get this model, right. So, if you stop with this, you already have beta, you already have solved the problem, as in like you have determined the coefficients, right. But here we are also interested in plotting, that is why we are discussing the rest of it, right. So, for these x values we need the y value, right. So, that we can find out using by passing this beta values, the model coefficient and the x values. Remember, that is what this format is, the model coefficients comma the x values, right. So, if we give that, we get this y plot, right. So, and then we can plot x plot comma y plot, r dot we can give, right. So, it will plot 1000 points, right. If you increase this number of points, you will get a smoother a smooth curve, right. And then we add the legend, right, because the first we had initially plotted the points and then the model, we write measured comma model, again within single quotes separated by a comma using the legend function. So, it will help us to plot this plot, right. So, that is how that is how we can use the NLin fit function to do nonlinear regression. So, again remember, if we are directly going to use prob over here, then we need to have the @ symbol over here, right. So, before concluding, a word of caution, right. So, this is as taken from numerical methods for engineers by Chapra and Canal. So, what we have been focusing in this part of the course is a simple derivation and practical use of equations to fit the data, right. However, there are lot of statistical assumptions which are inherent in linear least squares, which we have not discussed in detail. If you are interested, you can look into this reference, right, the book by Draper and Smith, right. So, some of the assumptions involved are each x has a fixed value, it is not random and is known without error, right. Only under this condition can we do linear regression, right. So, so for example, x and y we said, so if let us say if x is temperature and y is let us say some conversion, right. So, when we write 30 comma 0.8, what we actually mean is that this 30 is known precisely, that there is no error in this 30, right. There could be some error in this 0.8, which is what we are trying to find using linear regression model, which is why we are doing regression, that we want to find a model which best fits the data. So, there should not be any error in this x, right, and the y values are independent random variables and all of them have same variance. Similarly, the y values for a given x must be normally distributed. So, this y should be normally distributed. For the purpose of this course, right, whatever we have covered is sufficient, right, and most classical texts stop over here. but there are also other measures, right, which you can, if you are interested in regression, you can look into that as and when required, right. So, here we have limited ourselves to the simple derivation of linear regression and how to use it, provided the data satisfies all the assumptions that are required for linear regression. Right. These are some of the references that you can look into. This book by Chapra and Cannell. There is also applied numerical methods with MATLAB for engineers and scientists by Chapra, right. So, here you will find a lot of MATLAB related functions, right. There is also this book Matthews and Finks, particularly if you are looking for the derivation of the general linear least squares Z transpose Z into A is equal to Z transpose Y, right. So, that derivation is actually given in this book, right, and for advanced concepts of regression you can look into this Draper and Smith. Right. So, in this session we have seen what is regression, we saw what is linear regression. Linear regression we discussed three types: simple linear regression, multilinear regression and polynomial regression. All these three with model with constant coefficient and without the constant coefficient. Then we looked into some data transformation techniques. We subsequently saw how do we solve nonlinear regression problem, and then in MATLAB we learnt about 4 functions, right, polyfit, polyval, regress and nlinfit. So, regress is to be used for linear regression, right. Polyfit and polyval is to be used for polynomial fitting, whereas nlinfit is to be used for nonlinear regression, right. So, with that we will conclude this session. Thank you.